All right, everybody, hello. Today we are talking about ANOVAs, a very exciting topic. ANOVAs, all right, ANOVA is an acronym for Analysis of Variance. All right, so we're going to talk about ANOVAs in a few formats. Analysis of variance. And we've already been doing a sort of analysis of variance when we look at things like t-tests, but ANOVAs have a few more considerations and helpful applications that we will come to learn about. So first of all, what is it? I already gave it away, didn't I? But an ANOVA is an analysis of variance. We are focusing in on variance across groups specifically. So we're going to be really calling back to when we learned variance some time ago in our series of topics in this class. Variance relies on the sum of squares. Remember, the sum of squares is the sum of the squared deviation scores for a data set. So don't worry about that quite yet. We will go ahead and practice this when we get to our first ANOVA example. But here I have a very outdated meme about how ANOVAs are really just a combination of different sums of squares from different combinations of data from within the data sets that we're interested in making statements about. So that's what we're doing. We're analyzing variance or variation across data sets and within data sets. So we'll get to that in a moment. But an ANOVA requires some specific types of data in order for us to run one. We use an ANOVA when we can compare more than two groups, so 3 or more groups. We need a continuous dependent variable. Remember, a dependent variable is a sort of outcome of a study. And it requires a nominal or categorical independent variable. So something like this where we have groups, 3 groups, where we can look at the variability among and between these different groups. So we're going to start out with an example of comparing those who are unemployed, those who are employed part-time, and those who are employed full-time. So you can start to imagine these 3 different groups, and then we would measure some continuous dependent variable. In our case, we're going to measure satisfaction with one's career. So that's when we use an ANOVA, all right, and really, what do we end up doing with it? We're going to still run a hypothesis test, much like we've been doing all of this time. We're going to compare the statistic that we calculate, the F statistic, to the F distribution. So the F distribution is sort of a skewed distribution, all right? We see skew towards the right or a positive skew. And we're going to be looking over in that long, skinny tail. So the F statistic compares variance, right? It's an analysis of variance. So what this curve suggests is that if we get a large F value, there is very much variation between and within all of the groups that we are investigating. If we are not over there in the critical region, right, if we're over towards the left, that's support of the null hypothesis, which is going to be that all of the groups are the same. So let's take a look at these hypotheses here. Our hypotheses will look something like this. Depending on how many groups we have, we're going to say that each of those groups are equal, right? Our inference would be something like all of the population means that our samples belong to are the same, that they're all equal. But because the ANOVA is a bit of an involved test, it involves something called multiple comparisons. So say if we have 3 groups, we're going to be comparing group 1 to group 2, group 1 to group 3, group 2 to group 3. Right, we have a few different comparisons to make, and this only gets more complicated as we add more groups to the mix. So our alternative hypothesis for our purposes in this class is always going to be that at least one of the sample means is not equal. And you're actually going to write this out verbally because we're not making a specific prediction that the first group is different than the second or the second is different from the third. We're going to start with a blanket hypothesis, right? That just at least one of the groups is different. So we'll talk a little more about the limitations of this, but this is really what's limited to what we're willing to do by hand for this class. And then our labs elaborate a little bit on different types of hypotheses or predictions or findings that we can get from an ANOVA. All right, so I'm going to show you this next slide, and I'm going to, through the screen, all right, ask you not to panic when you see this slide. This is the formulas, plural, that we need to calculate the F statistic. So this looks just terrible, doesn't it? There are so many, all right? We have 7 formulas that we need to complete in order to calculate the F statistic. But again, I want you to not worry, because when we practice this, you'll see there's a sort of logical sequence to these events. So we'll just practice them, and I think you'll feel a little bit better. But we're ultimately trying to calculate an F statistic. So we've had Z, we've had T, now we're on to F. We're looking for an F statistic. So I'm going to go ahead and just talk through these formulas a little bit. The first one is an X with 2 bars over it. That's what we call a grand mean. So we're going to have 3 different groups, and we're going to have means for all 3 of those different groups. But then the grand mean is a combination of all of the data without any sort of group boundaries. All right, so that's our grand mean. Our grand mean is used in the sum of squares total. So to get the total sum of squared deviation scores for the entire set of data we're working with, we'll be taking each individual score and subtracting the grand mean, squaring it and summing it. All right, so very much like what we did for variance some time ago. Then we have the SS within, looking for the sum of squares within data sets. So we're going to have, in our example, 3 groups, right? I said unemployed, part-time, and full-time. So total is going to be looking at the data points from all of those groups. Within is going to be looking within each group, if that makes any sense. We'll be looking at deviation scores within the first group, then within the second group, then within the third. So then we have an SS between. The SS between is a combination, or at least a relationship, between the total sum of squares and the sum of squares within. And this is where it gets easier to calculate, all right? 2 and 3 are the back-breaking work, as we'll see. And then it's pretty much smooth sailing from here. The SS between is pretty quick to calculate, and then we collect some MS scores. We calculate for MS, which means mean square, which is also a variance measure. So what we're ultimately doing is getting the variance between or across our 3 groups, and then getting variance within each of those groups. And then F is a calculation that is the relationship between those 2 types of variance. Okay, I think we're ready. I think we're ready to try one. So let's go ahead and try one. I'm going to hop over to the whiteboard, and we're just going to work through one, all right? One step at a time. So let's go ahead and give this a try. So I've already alluded to what we're talking about here. We're talking about employment. So we're going to have 3 groups. And of the 3 groups, we're going to ask them, those who are unemployed, those who are employed part-time, and then those that are employed full-time. We're going to ask them on a scale of, let's say, 1 to 5, how satisfied are you with the current status of your career? So let's go ahead and do just that. So we're going to have 3 groups. I'm going to number them to help keep them straight. All right, so group 1 will be unemployed. Group 2 is our part-time employment. Group 3 is our full-time employment. And again, they're ranking on a scale of 1 to 5, how satisfied they are. So I have 3 scores for each. Here is one person that is highly satisfied with being unemployed. And then we'll go ahead and move on to our others here. Okay, so we have some data here. For each group, we're keeping it very small. You'll see that these calculations are a little bit heavy, so when it comes to us calculating these by hand, I try and keep it relatively light here. So, all right, we have 3 groups. So let's go ahead and think about our hypotheses. So remember our hypothesis testing steps. All right, I don't want to get too many numbers in here to confuse us, but we always start with our null and alternative, and then we'll find a cutoff score, and then we'll calculate, and then we'll decide. All right, then we'll decide what to do. So let's start by just getting our hypotheses in here. Let's kind of think about what we're testing here. So the null hypothesis for any ANOVA will be that all of these groups are equal. All right, there's no difference in career satisfaction across these 3 groups. All right, that's what we would say if we were to write this out verbally. Then the alternative, you're going to write it just like this. You're just going to say there's at least one difference. All right, so that means maybe there's a difference between unemployed and part-time people. Maybe there's a difference between unemployed and full-time people, maybe between part-time and full-time, but we're not specifying, all right? It gets complicated very quickly, especially if we have more than 3 groups. So we're gonna keep it simple. Another way that we're going to keep it simple is for ANOVAs, we are only going to test at alphas of 0.05, right? Only testing at alphas of 0.05. Okay, so we have our null and alternative hypotheses. Now maybe we want to get a cutoff score. So to get a cutoff score for the F distribution, we need something specific, all right? Well, we need the alpha level, and I already said that it's always going to be 0.05. We also need, we don't need tails, because this is always going to be what we consider a one-tailed test, because we're, remember, looking out on that funky tail of our F distribution. So what we really need to get our cutoff scores for the F distribution is degrees of freedom, all right, degrees of freedom. And we're going to get 2 different types of degrees of freedom. So there are a few comparisons we can make when it comes to an ANOVA, or when it comes to having multiple groups of data. So we can get variation between 2 groups, right? We can see how much variation there is between 2 groups, or we can see how much variance there is within one group. So we're going to get degrees of freedom between our groups and degrees of freedom within our groups. All right, so how do we do that? The degrees of freedom between is equal to k, well, extra line, and k minus 1. And k is new. So k is equal to the number of groups you have. All right, so we have 3 groups, but we could have more, right? We can have 4, 5, 6 groups in an ANOVA. But we have 3, so our degrees of freedom between would be equal to 2. Our degrees of freedom within is a little bit different. The degrees of freedom within takes n, and n is all of n, okay? So we could say have n1 is equal to 3, n2 is equal to 3, n3 is equal to 3, but ultimately our n is equal to 9. We have 9 data points here. So our degrees of freedom within is n minus k. So we have 9 data points minus 3 groups is equal to 6. All right, so this is a little bit different too, and a little bit funky compared to what we've done before. What we're going to do is we're going to take these two values and we're going to report them like this, okay? This isn't a fraction. This isn't anything that we're going to calculate. But we're just going to take the 2 and we're going to put our degrees of freedom between in the numerator and our degrees of freedom within in the denominator, all right? So it kind of looks like this. We got our numerator and our denominator, okay? Numerator, denominator. That's what we're doing here. Then we're going to take this over to the F table. We have a new table. So let's go look at that F table. So this entire table is specific to an alpha of 0.05. This is why we're not worried about an alpha of 0.01, because we need a separate table, and who wants to do that, right? We're just going to stick with this. So what do we need to do? We need to take those degrees of freedom that we just calculated, all right? So we need the degrees of freedom in the numerator. That's our degrees of freedom between. That's the number of groups we have. So if you look at this top row on the table, you see the numbers 1 through 10, as opposed to the rows here goes all the way down to 120, right, with some spaces in between. But the top row has to do with how many groups we have. So that's where we'll be in the second column for our degrees of freedom between. And then we need to go down to the 6th row, because we have 6 degrees of freedom within. So if we look in the second column, in the 6th row, we find a value like 5.14. 5.14. I'm going to write that down. Our F critical is equal to 5.14. Okay, so this is a little odd, a little different than what we've been doing, but we'll follow the same procedure every time we look up an F critical value from the F table. You get the degrees of freedom between and within and use them to look up our value on the table. Okay, so we've done the first step, we've done the second step. Now we're ready to calculate. We're going to calculate using that very long laundry list of formulas. But the first thing that we'll go ahead and do is get means for each of our groups. So let's go ahead and do just that. Let's get a mean for group 1, a mean for group 2, and a mean for group 3, right? So means, we've done them before, right? You add up all the values and you divide by 3. So for the first one, I'm going to add up 1, 2, and 5. I'm going to divide by 3 because there are 3 data points there. So we get a sum of 8 divided by 3 gives us 2.67. And if you can imagine group 2, the sum is also equal to 8. And we have 3 data points, so we would expect this to be equal. And if we calculate it, we find out that it is. And then our third group, if we sum these together, we get 3 plus 4 is 7, plus 2 is 9, divided by 3, we get 3. Okay, so sometimes I'll give this to you in the problem, but I trust that we can all calculate a mean now. So if they're not, that's what you do, a simple mean within each of the groups. Okay, so the first new thing that we need is called the grand mean. All right, the grand mean. If you look at the grand mean formula, it looks like this. It says G over N. G means to add up all of these values, okay, all of these values. So if we add up all 9 of these values and divide by 9, we would get the grand mean, and you're welcome to do so. But here's a little life hack, all right? If we already have the means over here, another way we can calculate the grand mean is just by adding all of these means together and dividing by 3, because there are 3 values here. All right, so we end up with a grand mean equal to something like 2.78. All right, 2.78 for our grand mean. Okay, all right, so I'm going to keep just stepping through the formula. So remember, don't get bogged down by all of the steps here because you have the formulas in front of you. Just take it one step at a time, right? The first thing we need to do is grab our grand mean and then move from there for the calculation step, right? So when you get to calculating. So we get our grand mean, and let's get a new slide here. So the next thing after our grand mean will be the SS total. The SS total uses the grand mean in its calculation. It looks like this. SS total is equal to the sum of our x values minus the grand mean squared, all right? So what we're going to do is take each x value, subtract the grand mean, and square it. All right, so I will go ahead and do just that. And while I do, I will tell you about how. If you look up how to do an ANOVA, all right, if you go online and start to look around at this, you'll notice that there is a lot of different information. There are lots of different ways to calculate an ANOVA, all right? This is the way that I find to be simplest, all right? So this is what I choose to share with you. And as we move through it, you might think to yourself, wow, this doesn't seem simple at all. And that's really because this is not a simple test. We're doing lots of different comparisons here. So while a little long, while a little tedious, I trust that we can do it, all right? This is just a pep talk, basically. Don't get overwhelmed. Don't get bogged down. Because this is, I would say, all right, and don't quote me on this, but I think this is the most difficult test that we do in this class. So just don't get overwhelmed, right? Just take it one step at a time, and we'll do plenty of practice with it. So what I'm doing here, okay, is I'm taking each of our values and I'm moving in order by group. So if we go back in group 1, we have scores of 1, 2, and 5. So I took 1, 2, and 5, and I subtracted the grand mean from each, and I started down on a new row for group 2, and then again for group 3. So then what we would do, all right, is we would follow order of operations. So we would want to complete what is inside of these parentheses first. So for the first one, we would take 1 minus 2.78. We would get a value like 1.78. We would square that value and we would get a number. We would get something like 3.1684, okay? And then we would do the same for each. So I'm not going to do these right now. I do this in a homework review. But I'll go ahead and let you try this out for yourself, all right? Just take your time and solve for each of these here. And then once you do, we're going to sum it all up, right? That's what the equation asks us to do. So when we sum this all up, we get a sum of squares for the total data set equal to 13.6. All right, 13.6. So this value is not going to be too meaningful yet, so let's just hang on to it, all right? Let's keep it in our heads. We'll keep it here, and I'll go ahead and start up on a new slide here. So if we're just moving in order of those formulas, all right, the next one we'll want to do is the sum of squares within. And as promised, this is the only other one that's a little bit heavy, all right? It's a little bit involved like the one we just did. And it's similar but a little bit different to what we just did. So we're going to take group 1, we're going to take all the x's in group 1, and we're going to subtract the mean of group 1, okay? So not the grand mean anymore, but the mean that's specific to group 1, and we'll square it. And we'll go ahead and do this for each of the groups that we have. So if we had 4 groups, we would do this for all 4 groups. But we only have 3 groups, so we're going to do it for our 3 groups. So the scores in the first group are 1, 2, and 5. And we have a mean in the first group of 2.67. So I would go ahead and take that first score, 1 minus 2.67 squared plus 2 minus 2.67 squared plus 5 minus 2.67 squared. That's our unemployed person that's very satisfied with being unemployed. So the second group has the same mean. All right, its mean is also 2.67 squared. So we have a score of 2, a score of 4, and a score of 2. All right, and then in our last group, our mean is equal to 3. So we have 2 minus 3. All right, we'll keep it consistent. We have 3 minus 3. All right, I guess we can expect what we would get here, right? That means that there's no deviation from the mean for that particular score. And then we take 4 minus 3 squared. All right, so same story goes here. You would get the difference for each of these. All right, so you would get the differences within each set of parentheses. You would square them, and you would do that for all 9 values and then sum them up. And if you do so, you should get something like 13.3. All right, something like 13.3. So we had 13.6, now we have 13.3. So let's go ahead and move on to our next calculation. I will go ahead and do it right here on the same slide. So the SS between, this is where things start to get a little bit easier in my opinion. The SS between is the difference between the SS total and our SS within. All right, so we get something like, all right, we get something like our 13.6 minus 13.3. All right, so let's go ahead and do that. So we have 13.6 minus 13.3. All right, and what does that give us? That gives us a difference of 0.3. All right, of 0.3. Okay, so then we move on to our mean squares. So remember, our mean squares are going to be a sort of sum of the variance between our groups and within our groups. So those calculations look something like this. And again, I know this is a lot, all right? I'm not pretending it's not, but just look to our steps, all right? Look to our steps and just notice that each formula sort of builds on a previous one. So here we need the sum of squares between, which we just calculated, and we're going to put that over the degrees of freedom between. All right, so this is equal to 0.3 over 2. All right, and if we go ahead and calculate that, we get something like 0.15. All right, 0.15, so this is the MS between. And let's go ahead and get the MS within too. So same story here. We're taking the sum of squares within over the degrees of freedom within. And if you're wondering where I'm getting those degrees of freedom from, it's all the way back, all right, all the way back here. All right, our degrees of freedom between are right here and within are right here. So I'm going to go ahead and take our sum of squares within, which was that 13.3. I'm going to divide by our degrees of freedom within, which is 6, and this is going to give us something like 2.2. And then the moment we've all been waiting for, okay, our F is equal to the mean square between over the mean square within. All right, and now we have those values. We have 0.15 and we have 2.2. And what does that give us? It gives us an F that looks something like this. It's a long decimal, so remember you can round this because think about the decision we're going to make at the end of the day. It's not going to impact that decision we're making about the null hypothesis, but I get something that looks like this. All right, so if you round this, that is quite all right. But we get something that looks like this. All right, it kind of goes on and on. All right, so this is our final F value. All right, our final F value. So just like our other hypothesis tests, we want to take this F value and compare it to our critical value. All right, and what was our critical value? We have to kind of take a long trek back here. Our critical value was 5.14. So let's think about, let's go ahead and get a sort of weird F distribution here. Okay, so it's like this with a big long tail out this way. All right, so anything over here, anything past that 5.14, this would indicate that there is so much variance across our three groups that we do not consider them equal. But if we find anything over here, right, not beyond 5.14, we would say, hey, the groups don't vary enough for us to consider them to be different. So what does that mean for our score here? Well, our score certainly does not exceed or fall into our critical region, huh? It falls somewhere, get rid of that line, it falls somewhere over here, right? So if we trek all the way back to our hypotheses, all right, we would have to retain that null, right? We do not have any evidence that the null is untrue. We would retain the null. We would say there's no difference, or there's no evidence that there's difference in employment or career satisfaction across these three levels of employment. Feels like an awful lot of work to get a non-significant result, right? But hey, welcome to science, right? I feel like these classes or statistics or examples about learning statistics, they build you up to believe that significant differences happen all the time, when they really don't. They're unlikely to occur by definition. So there we have it. There's our first ANOVA, okay? A nice long procedure here. Let's go ahead and try one more. All right, let's try one more. I'll move through this one a little bit quicker this time. Well, maybe. I always say that, and then I feel like I never do. But let's go ahead and look at another couple of groups. So we're going to have three groups again, but we're going to have a little more data in each of these groups. So this example is about drug use and driving ability. All right, so we're going to see people's driving ability while using alcohol. We're going to see people's driving ability while using, let's call it Mary J for short, right? Marijuana. And then let's also look at a control group, right? A control group. So a control group meaning a sober group under the influence of nothing, right? So studies on this are done. There are specific driving ranges and safety protocols in place where we can test driving ability under the influence of various substances. It's important information, right? It's a public safety issue. So let's think about how we might analyze this using an ANOVA. So let's say that we get a driving ability score somewhere between, let's say it's a 1 to 10 scale. And I'll go ahead and put the scores here for each group. All right, so a 3, a 4, a 1, and a 3. For marijuana, we got a 1, a 6, a 4, and a 3. And for the control group, we have something like this. So you can already probably start to notice, right, that the data in these groups is a bit different, right? But we can't make too many statements about it yet. We need to do a little bit more. So let's go ahead and start by setting up just our basic hypotheses again. All right, so the null hypothesis for an ANOVA is always going to be such that all of these groups are equal, all right? No significant differences across the groups. The null will be at least one difference. And then we are testing this again. All of our ANOVAs for our purposes will be tested at an alpha of 0.05. Okay, so let's go ahead and get our hypothesis testing steps over here again, because I like to have them around. So, all right, so we did this. All right, so let's move on to cutoff scores. All right, how do we get cutoff scores? So remember, this is always a technically one-tailed test, and I'm giving you the alpha level. So all we really need to concern ourselves with here is degrees of freedom, and not just one type, but we need the degrees of freedom between our groups and degrees of freedom within our groups. So the degrees of freedom between our groups is our number of groups minus 1. So in this case, 3 minus 1, all right, equal to 2. And our degrees of freedom within is equal to n minus k. So n minus k. So how much data do we have total? We have n equal to 5 in each of these groups. So n1, n2, and n3 all equal to 5. So we have a total n of 15. So we're taking 15 minus our number of groups. So our degrees of freedom within is 12. All right, so remember, we take these values and we kind of think of them this way. And we take them over to the F table. So let's hop over to the F table and take a look. So we're still in the second column because our degrees of freedom between, up in the numerator, is 2, but we need to scroll down a little further this time. We need to look to 12 degrees of freedom within, or in the denominator. So we're in the second column in the 12th row. If we go there, we should find a value like 3.89. 3.89. So let's go ahead and write that down. I'm going to write down our F critical. So F critical is equal to 3.89. All right. Well, then I think we're ready to move forward, aren't we? We got our cutoff scores. All right, so we got our cutoffs. And now let's start to calculate. So again, the first thing we'll want is group means and a grand mean. So sometimes the group means will be given to you, sometimes not. So let's go ahead and get our group means in here. And then let's get our grand mean down here too. All right, so what are our means here? So remember, for means, we're adding all of these scores together. So 1, 2, 3, 4, 5 scores. We would add all of these together and divide by 5. We would do that for each group, and we would get some averages like this. So remember, averages are awesome descriptive statistics. We can take a look here and already see, okay, the control group scored higher than the marijuana group, scored higher than the alcohol group. But we're going to continue to test this to see where the differences really lie, okay? So remember, for the grand mean, you can add up all 15 of these values up here, all right, and divide by 15. That would be one way. Another way is you can add up these 3 means, okay, and divide by 3. So that's usually what I prefer to do, because if we have the means anyway, it just simplifies things a bit. But regardless, we're getting a grand mean, or a mean for all of the data. So you want to make sure it makes some sense, right? If you get a crazy number here like 10, that doesn't seem like a very representative average of this group, does it? So there we have it, all right, a grand mean. So remember, that's the first thing we want to calculate. And then if we just continue down the line of all of the values that we need, the SS total comes to mind next, because we're getting a sum of each score minus the grand mean squared. So let's go ahead and start to do this. All right, so in our first group, we have 5 scores, 3, 4, 1, 1, and 3. We are going to take each of them minus our mean here. All right, 4.26. Needed to check myself. 4.26. All right, so we're taking 4 minus 4.26. We're taking, hold on, I'm already going to run out of room. All right, so this is the hardest part of the ANOVA. It's not the math. It's making sure you have enough space for all of your calculations. All right, so we're taking 1 minus 4.26, 1 minus 4.26, and of course we're squaring all of these. I'm getting lazy. All right, we're squaring all of these, and then lastly, for our first group, there we have it. Now let's move on to the second group. We have 1, 6, 4, 4, and 3, and we're still taking the grand mean from each of these. So 1 minus 4.26. All right, we have, sorry, my brain. It's you know, I'll tell you, the ANOVAs are not hard to do. They're not hard to do, but they just require attention, right? They require attention, focus, practice. So hopefully my, you know, seeing the slowness in which I move through these and the kind of patience here rubs off on you, because it really is needed for calculations like this. All right, so now I'm on to the third group. So we have 8, 7, 8, 5, and 6. So we're taking 8 minus 4.26 squared. We're taking 7 minus 4.26 squared. We're taking 8 again minus 4.26 squared. And again, I know this is messy. I do apologize. So let me know if any of this needs to be clarified. 5 minus 4.26 squared. And then lastly, we have 6 minus 4.26 squared. Okay, whew, that was a lot, wasn't it? So let me go ahead and show you what I didn't do the last time, which is showing you what you get when you get your different scores here. All right, so if you take your different score here and square it, what do you get? So I'll go ahead and write out the values that I got here. Okay, 0.0676 plus 10.6276. All right, so this will take me a while to kind of write out here for you, but it's a good way for you to check your work. And if you say get to the end of an ANOVA and realize that you have something a little bit different than me, it was likely just a little math oopsies, right? It happens to all of us. So just be sure that you're checking your work and taking your time. See, I almost made an oopsies there. Okay, 0.0676 plus 0.0676 plus 1.57876. So notice that there's sort of a pattern here too as well, and numbers that repeat because we have the same different score squared. So catching on to those patterns can also help to make this a little bit easier for us. So here I go, on and on. Okay. So again, math isn't hard, but the organization can be a little bit, it's a lot to keep track of, but just take your time. All right, here we go. So now we have what we need to calculate our sum of squares total. So let's go ahead and do that. So our sum of squares total is equal to 78.934, or something close to it, right? Remember, our rounding might not be identical. In fact, this 4.26, you might have just as well done 4.27 because of rounding. That is okay. All right, that is all right. Okay, so here we have it, our sum of squares total. All right, so that's the first of our somewhat challenging values to get. All right, so let's just go ahead and jump right into the next, which is the sum of squares within. All right, so the sum of squares within is also a little bit involved. So let's go ahead and bang that one out. So the sum of squares within is very similar to what we just calculated, except instead of taking the grand mean as the difference, you're taking the mean of each of your groups, all right? So in this case, we have 3 groups, so we're going to take the differences this way. All right, so x bar 3 squared. All right, so this is what we're going to do. So we calculated those means before. The mean for group 1 is 2.4, the mean for group 2 is 3.6, the mean for group 3 is 6.8. All right, so we're going to use those same values and we're going to take their relevant mean from them. So 3 minus 2.4 squared plus 4 minus 2.4 squared plus 1 minus 2.4 squared plus 1 minus 2.4 squared. You know what I would like to hear from you when we talk about this is if doing this type of kind of repetitive work like relaxes you, or if you like it. I get some mixed opinions on this. I myself, as you might imagine, kind of doing this a lot. All right, now I moved on to the second group. All right, so this is the second group's mean and the second group's data. So now we're doing a mean of 3.6. But doing this, I think once you get in the groove of it, can actually be quite nice, right? It's almost like mind-numbing in a good way. Maybe that's not fair to say. You can argue with me if you want, but that's how I feel. Okay, so we got another 4. We're subtracting that 3.6. Mean for group 2, so 3 minus 3.6. All right, now we're on to the last group where our mean was 6.8, so we have an 8 minus 6.8. We have a 7 minus 6.8. We have another 8 minus 6.8. All right, we have a 5 minus 6.8. And we have a 6 minus 6.8 squared. And then that concludes it for us. And again, I will go ahead and put in the decimals I got after I did this math so that you can check yourself. But that's just more time that you gotta watch me sloppily write on this. Whoop, we need a plus sign. Sloppily write on this drawing pad here. So don't mind me while I get these in here. All right, 0.36. 6.76 plus 5.76 plus 0.16, 0.16 plus 0.36. All right, 1.44 plus 0.04 plus 1.44. Be sure to take care of your hands at this point so they're not cramping up on you. Take a break, go get a snack. All right, so here we have it. All right. This is how we get our sum of squares within, and remember, this is sort of the last of the big ones, okay? So once you get through the sum of squares total and the sum of squares within, the rest of the math is pretty quick. So what do we get here, all right? So we had 78.934. What do we get here? We get 27.2. All right, and remember, your rounding might not be exactly the same as mine, and that's okay. All right. Let's go ahead and finish this off then. Let's get it done. So now we want to get our SS between. All right, so our SS between is the relationship between the SS total and the SS within. So let's go ahead and get that SS between. It is equal to the SS total minus the SS within. So in our case, it is 78.934 minus 27.2, which is equal to 51.734. Again, your rounding might be a little different depending on how you've been rounding along the way. So let's go ahead and get our MS between and our MS within. All right, so these are similar. We take the SS between over DF between, so sum of squares over degrees of freedom, and we do the same thing here, but with our within subjects, right, or within groups information. So we have our between sum of squares right here, right? It's our 51.734. And if we want to grab our degrees of freedom, we have to hop all the way back here. Remember, our degrees of freedom is 2 because we took our number of groups minus 1. Our degrees of freedom within is 12 because it's our total number of data points minus our number of groups. Okay, so 51.734, we're going to put that over 2. We get 25.867. We're going to do the same down here for the sum of squares within. We get 27.2 all over 12, because that was our degrees of freedom within, and we get 2.26. Okay. Oh, in the moment we've all been waiting for. We're fatigued. We're ready to figure this out, right? So we take our mean square between over our mean square within, all right? 2.2, I think I changed my value somewhere along the way here. This is another one where, depending on where you round, but all's well that ends well. Okay, we're all going to get, if we've done this correctly, or you know, at least very close to, we're going to get an F that looks like this, 11.41. All right, 11.41. So let's go hop back to our critical value, all right? And let's go ahead and get a funky little F curve here. So we needed to exceed 3.89, all right? So did we do it? I think we did, right? 11.41 would most certainly be somewhere over here, all right? And what does that mean? It means we reject that null, all right? We reject the null. Then we have evidence to suggest that at least one group is different. So what group is different, right? That's not something that we're going to determine by hand. That would be an awful lot of work. We won't even get into it, right? We'll leave that to SPSS. But what we can do is once we get to this point is we can go look back to our means, all right? Look at our means here. Which one seems to be different? Which one's suspect to you, right? It seems as though this score is quite a bit higher than these other two scores. But that, of course, is just an assumption, right, by just looking at the descriptive statistics. So if you wanted to actually determine where the significant differences are here, you would have to run what we call a post hoc test. We run a specific test called a Tukey test, which does multiple comparisons to see where the significant differences are within these groups. And we'll be doing that in one of our labs, so you'll get some exposure to that. But this is where our hand calculation stops, all right? And I hope that you're happy with that. Okay, so those are our two examples. So we're going to hop back to the slides for a minute. And we're going to talk about just a couple more things having to do with ANOVAs before we wrap up here. All right, so the next thing we'll take a look at is basically a shortcut to solving ANOVAs, and something that we'll get some practice with again on another homework here. So I'll kind of leave this to you to sort out. But what we have here is solving an ANOVA from a source table, so from some information that's already given. So here we have an example where we have data from 3 types of treatment for dementia, cognitive therapy, an oral medication, and then a combination of both. That's what we're interested in comparing across groups. So what do I mean by source table? I mean this data, this type of information here, where we have the number of individuals in each group, where we have the sum of the x's in each group, where we have means for each group. But then more importantly, if I give you something like this, a source table like this, where the SS total and the SS within are given, all right, those are the big hard ones to calculate. You should be able to take the difference of those two sums of squares to find the sum of squares between, and you should be able to complete the rest of the calculations to F. So you would also get your degrees of freedom. You would figure your degrees of freedom by looking here, right? How many groups do I have and what is my total N? So I'll leave this to you to do, and we do have a homework. Our homework 11 is all about this. So just a note that you're not always going to have to be doing these from the very beginning, right? It's a lot of work, it's a lot of math. So we kind of use these to help us practice the logic of ANOVAs without all of the number crunching, right? Just kind of moving from sum of squares to the F statistic and then making decisions. So go ahead and give this one a shot if you want some practice, and we'll practice on homework 11 as well. And then just one more thing. So we've been talking about one-way ANOVAs, right? An ANOVA type called one-way ANOVAs, in which we're looking at one categorical variable. So remember, the word variable means that it can vary. So one categorical variable could be employment status, and within that variable we can have unemployed, part-time, and full-time employed individuals. But say that we add in another categorical variable that you could also belong to. Maybe we want to look at part-time, full-time, and unemployed individuals, and we also want to compare across gender, right, male and female. You can belong to both of those categories, and we have a type of ANOVA, or called a factorial analysis, that lets us do this. So we can have two sets of categorical independent variables. So we have an example here of caffeine, having some caffeine versus no caffeine, and maybe say energy in the morning and afternoon as the dependent variable. So you can belong to two of these categories at any given time, right? You could have been given some caffeine and asked your energy level in the morning or in the afternoon. You could have had no caffeine and asked your energy level in the morning or afternoon. So we have a lab that goes over the two-way ANOVA, but this is not something that we will calculate by hand because, as you can guess, it's complicated. We have lots of multiple comparisons. We're comparing across multiple independent variables and one dependent variable. But this is an idea of what it looks like, and you need to know that we are capable of doing it. So the very last thing I'll leave you on is this, which I think is just so cute, all right? It says, in the whole scheme of things, are we really so different? And that's what the ANOVA is all about, is taking multiple groups of data and comparing them, not just their means, but their variance, to see if they're truly different. And I think, in addition to this being adorable and cute, I think it does a good job of explaining just that, right? We have a sort of tall, skinny distribution where we don't have as much variance, a very low distribution where there's lots of variance, and then a more normal distribution, right? So we're accounting for a lot of different things when we run an ANOVA, which is why it's a relatively complicated test. But there we have it. That's our overview of ANOVAs. So we do quite a bit of work on ANOVAs via homework assignments and lab assignments. So this is not the last time you'll see them. So as always, be in touch if you have any questions on this material.